So welcome everyone to today's robust optimization webinar. It's my great pleasure to introduce the first speaker, Eva Ley. Eva is a PhD researcher at the Technical University Braunschweig in Germany. She did her bachelor in applied mathematics at the University of Trier in Germany, did a bit of an exchange semester at the University of Southampton, and then for the master joined TU Munich, and now at TU Braunschweig, she's working on robust optimization and bi-level optimization, including discrete problems. So without further ado, I want to give the control of the mic and the speaker to you, Eva.
Yeah, thank you. Thank you for this introduction and the invitation to speak here. And I will talk about budget deflection and optimization under controllable uncertainty. And this is a joint work with Rebecca Marx, Maximilian Merkert, Tim Niemann, and Sebastian Stiller. So first of all, as a motivation, we have some optimization problems with uncertainty, where in the following I will assume that we only have uncertain costs, and I assume that the cost coefficients lie in some intervals that we know that are closed and bounded. And then we obviously can write the realization of an uncertainty as a 0,1 value, or a value in the 0,1 interval. And well, if we now have, for example, a known uncertainty set like this budgeted uncertainty set here, we all know in this webinar one approach to deal with this, and this is simply using robust optimization. So we solve our problem for the worst case outcome. And in such a small example like the shortest path problem, or actually would be a selection problem, we would choose the lower edge because this has the smaller worst case outcome. Obviously, in a setting where we could choose a mixed strategy, depending on now, for example, in this budgeted uncertainty set, the gamma, we might also choose a combination of those two choices. Now, in a lot of real-world applications, it might be possible to reduce the uncertainty, for example, by doing some measurements or paying some insurance or paying an opponent in some case. And there are a few problem settings that have been studied using dependent uncertainty sets. And here are two examples that also have been shown in this webinar. So as a first example, I've got here this decision-dependent uncertainty, or also called an endogenous uncertainty or uncertainty reduction in robust optimization, where we have some choice X, which is often assumed to be binary, and with which we can reduce some upper bound on the uncertainty U, and only then also at the same time solve our robust optimization problem. And here and also in subsequent slides, you should understand this dot as element-wise product. So we have really element-wise some upper bounds here that we can reduce if we set the according X to 1, but then we might have some costs for this query. Now, another setting that we can have with dependent uncertainty sets that has been studied and also presented here is decision-dependent information discovery, where we can choose some elements, some coordinates, also via binary choice, that where the information, where the uncertainty is realized before we then solve our optimization problem. And then we, need to make sure when the remaining uncertainty realizes that the choices are, for the uncertainties which have been revealed before are really fixed to the according values. Now, what I want to do in the following is that I want to first introduce some kind of decision-dependent uncertainty set, controllable uncertainty, where we really can control these uncertain intervals. So we really want to reduce them element-wise. And at most, such a reduction can happen to only contain only a single point that we will call hatching point. And then later on, I will want to have a look at two different settings, one where these hatching points are known, where they are some parameters to the problem, and a second one where they are unknown. And then for those two settings, I want to have a look whether budget deflection can occur. So budget deflection is a setting where we actually query some element that we will never use. And this might seem unwanted, and it can happen in one of the two settings. And in this setting, we will show or have a look what we can do to prevent it and what happens then. So first of all, for controllable uncertainty, so here's again our interval, and I will, as everything is element-wise now, only always focus on just an arbitrary element, and this will be similar for the other ones in my optimization problem, where we now have this interval for the cost coefficient. And if we say we want to query some element completely, so I will again use an x for this decision, then well, the whole interval is reduced to a single point, and we can give this point by a value be in the 0-1 interval, and this is called the hedging point. Now, this might be a too strict scenario or dependency in some settings, so we only want, so we want to relax now this assumption that queries were 0 or 1 to be also fractional values in the 0-1 interval. And then the interval should be reduced accordingly so that the upper bound increases to xe times be, and the lower bound is decreased to 1 minus xe times 1 minus be, where, well, this 1 minus be is simply the size of this remaining interval. Now, still, we here assume a linear dependence of the query to the uncertainty reduction. So this is still maybe a too strict assumption. So we now want to introduce some query outcome functions such that the queries can have arbitrary dependency with the reduction. And this also might be different for the lower bound and the upper bound. So I really introduce these query outcome functions phi le and phi ue. But obviously, if they can be equal, and I will just drop the sup and superscripts if they are equal. Now, for these query outcome functions, well, we have the assumption that they map into the 0-1 interval. And then we add some further assumption that depending on the setting, we will just get without loss of generality that they're monotone. And that, well, if we don't query anything, then the query outcome function should also be 0. Now with this, I can, depending on the choice of the query outcome function, model different behaviors. For example, still again, the linear behavior here on the 0-1 interval. I could, in the result model some binary outcome by using such a step function, but I can also choose some asymptotic behavior, some asymptotic function, such that this hedging point is only reached in the limit, and even this might not be necessary. So also this is not necessarily the case. So wrapping all things up that I've introduced now, we have for some uncertainty set U, the controllable uncertainty set with respect to a query X and a hedging point B, defined as those elements in the uncertainty set that also lie within this bound, so that are at least phi le of xe times be, and at most 1 minus phi ue of xe times be, and this should hold for all the coordinates. Now, with this, we can define different settings. So far, we only have some uncertainty set that is dependent on some decisions and maybe on some parameters. And as a first setting, I want to assume that the hedging points are known, so that this is a parameter to my problem. And then I want to now consider the following problem, that on the first stage, we minimize, so our choice is, our reason is to minimize. We first choose some query X, then the remaining uncertainty realizes, and in the last step only, we solve our problem Y, and that we now have some query costs similar to a previous example, which are non-negative, and then the according costs for our underlying optimization problem. Now, this problem is very similar to a problem that I showed you at the beginning under an additional assumption, and that is if this set Y is non-empty and convex, then this problem KHP has the same optimal objective value as if I just choose those two innermost decision stages, so that we really have this problem setting of uncertainty reduction and robust optimization that was also studied by Aslan and Post, and where you can find a robust optimization webinar talk also online, I think. So under this assumption, you can always also just think about their setting, and then we have some solution methods from them. We have some complexity results. Well, under the additional assumptions that we only have upper bounds on the uncertainty, so that the phi LE is 0 for all elements E, and they also have the assumption that X is binary, which we don't need in the following. Now, with this problem setting, I've got here an example where we will see that it is actually optimal to query an element that is never used. So let's start with the example. So this is the shortest path problem on this very simple graph, actually a selection problem between choices, where we have some uncertain cost coefficients in some interval 3 to 7, respectively 1 to 5, where we have the hedging point for both elements at 1/2, and where we have some linear query costs with query cost coefficients 1/2 and 1/4. Now, I just set the query set to be just the unit cube, and the query outcome function should be both the lower and the upper one, also both for the first and the second edge be just XE, so that we have this linear dependence that we had at the very beginning. As an uncertainty set, I assume to have the budgeted uncertainty set with budget 1 with a gamma equal to 1. And then we can have a look at this problem now, where we want to minimize our objective function and have in the first stage the choice over the X, over the query, then the realization of the uncertainty that is dependent on our X, and then finally want to choose which path to take. Now, if we really have the minimization over the Y in the last step, we could also just relax here the Y to be not binary, but in just the 0-1 intervals. And then we could also swap so that we have a setting nearly similar to the uncertainty reduction and robust optimization setting. Now, if we want to solve this, we might just start now with a few choices of X and see what's happening then. So if we don't have any query, we basically have the kind of robust setting where we have swapped here, and when we could now in the when we swapped it would need to allow some mixed strategies. So here the maximization step, or the uncertainty, will realize in such a manner that both the choices, both the paths have the same weight, and this is the case if for the first edge is 1/4, then we have a cost of 4 here, and 3/4 for the second one, because then we also have a cost of 4 here, and then it doesn't matter which choice we take, and the objective is 0 plus 4 equal to 4. The 0 just comes from our query costs, but we don't have them here. Now, we could just arbitrarily say, okay, let's see what's happening if the second query is 1/2. Well, then actually the uncertainty will realize in exactly the same manner. We again can choose either path for as an optimal solution, but now we have this additional 1/4 of the query costs here in the objective, so this solution is obviously worse. Now, if we, instead of only half querying the second coordinate, really query the second or coordinate completely, then we fix the uncertainty for this edge to the budget to the hedging point, so that we have a cost of 3 here. And what's happening to the first uncertainty could be basically anything from 0 to 0.5. If it was 0, we would again have both edges as an optimal solution, but as soon as it is positive, we only have the second edge as an optimal solution. And then we have an objective now of the 0.5 from the query cost plus 3, which are now the costs for this edge. So we have actually really improved our objective here, but we can still do something better. And this is also the optimal solution. And that is that we only completely query the first edge, because then we again have an uncertainty, especially for the second coordinate of 0.5, because we now have first fixed the uncertainty of this first edge to the hedging point, to the 0.5 here. And then because we only had a budget of 1 for the uncertainty, also the second the uncertainty of the second edge is fixed to 1/2. So then we have again the same solution and now a better objective because the query costs were smaller. But we have now queried an element, this upper edge, that we would actually never use in this setting. So this is what we call budget deflection. More formally, we have the following definition. So we say that an optimization problem with controllable uncertainty, where we have non-negative and element-wise query costs and where the query costs for 0 are 0, where we have an optimal query x star from some query set x that is assumed to be downwards monotone. And if we now denote y star of x star as the set of all solutions of the underlying problem that are optimal for at least one realization of the uncertainty, once this x star has been fixed, then we say that an instance allows for budget deflection if there exists a coordinate with positive costs, so a coordinate that we really query. That, however, is never used. So where we have y e star equal to 0 for all optimal solutions here. So in short, we have budget deflection for the KHB setting, as we just saw with the previous example. Now, this might seem a bit strange, and if we really think about the uncertainty as an uncertainty and not as an opponent, this probably does not make too much sense. So we maybe want to prevent it, and we can show that we can prevent this by really setting this lower query outcome function to 0. So if we have done this, if we have now some downwards monotone query set and uncertainty set, again with query costs that are non-negative element-wise and 0 for no query, then if we have in an optimal solution the query costs being positive for some element where the lower query outcome function is 0, then we will always find some optimal solution, some optimal realization of the uncertainty such that we really have some optimal solution y star where we choose this element. Now, if we want to prevent budget deflection, we can just modify our model by setting the lower query outcome functions to 0, and then we don't need to worry whether we could have this effect anymore. Now, if we change our model in such a way, or in general, if we just replace our query outcome functions by some smaller query outcome functions, or just the same ones, then the optimal objective value might increase because we reduce our uncertainty intervals less, and then, well, the opponent, the uncertainty, has more chances to realize in a bad way for us. So in particular, if we set the lower query outcome function to 0, our optimal objective value might increase. Now, this is the setting with the known hedging point that I wanted to talk about. And in the last minutes, I only want to shortly touch upon a setting with unknown hedging points. Now, where we have a really similar setting to the decision-dependent information discovery setting that has been studied by Omar Poss and Rogier, where we have some choice, some queries first. Then, so if we first decide which and by how much we want to reduce this uncertain intervals, or these intervals for our uncertain costs, then we have, in a worst case manner, the choice or the decision where this smaller interval actually lies, so where the hedging point is, and then we solve the remaining robust problem. So first decide what our solution of the underlying problem is, and then the remaining uncertainty realizes. Now, in this setting, The short answer is that we cannot have any budget deflection. So here we don't need to worry about such maybe unwanted behavior in an optimal solution if we have also query outcome functions, lower query outcome functions that are maybe positive for some queries. So yeah, to be more exact, if we have some downwards monotone query set X, some query costs that are negative element-wise, and again 0 for no query, and some optimal solution X star for an instance of UHP, then if we have an element with positive query costs, then there also exists some hedging points, some optimal hedging points, such that an optimal solution exists where we really use this element. So to wrap up, I introduced the controllable uncertainty set as a type of decision-dependent uncertainty set where we reduce the uncertainty by reducing the intervals where the cost coefficients lie in. And then we saw that we can have this effect of budget deflection where we query some element that we actually never use in any optimal solution in the setting of KHP, so in this first setting, but this cannot happen in the second setting, UHP. This is also written down in our preprint robust optimization under controllable uncertainty that you can find on Optimization Online. And with this, I want to thank you.